Okay, ladies and gentlemen, thanks for joining me today. Actually, the tutorial Fred was talking about, because I'm currently at the Rams symposium. Actually, had quite a few people turn up to tutorial and say hello afterwards and say, "Oh, I've had," one guy said, "I've had lots of one-way conversations with you," and I said, initially that's a bad thing, or at least when people have one-way conversations in my line of work, that usually means that someone's listening while the other one's talking about what they did wrong. So, but what he meant was that he has listens to the webinar or listens to the podcast and which is a webinar. So it's really good to see people turn up after hanging out with me virtually for a while. So today's conversation is going to be about this thing called the log-normal distribution. I'm going to do a little bit of revision from a previous webinar about the normal distribution or bell curve, but it's not required or prerequisite knowledge to get through the conversation we're about to have today. I'll ask in advance too, just a little bit of admin thing. Fred, if someone jumps in, has a question or something that needs to be answered, could you let me know using your voice because I'm doing this remotely in a hotel. I don't have my second monitor to be able to keep on top of all the comings and goings. So on that note,
Will do.
thank you, sir. On the log normal distribution, some people may have heard of it, some people might not have heard of it, and some people will see that in the title log normal there is the word normal. So let's talk about what the log normal distribution is, and we're going to start by going and talking about the bell shape that we see in the world around us, the bell curve, which is, some of you might know, is essentially the shape of the PDF curve for the normal distribution. Anyway, so what is this nonsense? Let's say I've invented a random variable, x, which has an absurd probability density function. When I say random variable, that can be something like time to failure or the amount of ice cream I eat every day, which is pretty random, but pretty significant if I had my way. So let's just say x is some absurd random variable like the weight of unicorns, just something truly absurd. And what I mean by absurd is I'm going to create a probability density function for this absurd random variable like this. And this is a curve that we often see to characterize random variables. And I've made one that's so clearly non-natural, where it has a square shape on the left side and a triangle shape on the right side. So hopefully you can agree with me that this is not something you'd expect to see in the natural world around us or reliability engineering and so on. So what I'm doing now is I'm creating this absurd random variable, which clearly has no realistic shape to its probability density function, which describes the likelihood of random variables having specific values. And we're going to do something with this random variable, namely add it to itself. So let's just say this random variable represents the mass of unicorns or something that's completely absurd. And this scenario you can see on the screen represents us adding the weight of two unicorns together. So if we selected one unicorn, we'd weigh that unicorn. So, okay, random variable number one. Select another unicorn at random. Okay, weigh that unicorn. That's random variable number two, but they're the same random variable in that they represent the same process. Now, when we add these two random variables together, the mass of two unicorns actually tends to just be described in a slightly different way. If we get our computer to help us describe the distribution of the mass of two unicorns, then we get a curve which looks like this. It's clearly not happy or healthy. It's still got some stuff going on. It's clearly not a triangle or a rectangle anymore. And it's clearly getting a bit smoother, dare I say, a little bit bell-shaped, even though there's a few things jutting out. So this is what the distribution of the mass of two unicorns looks like. And we can keep going. This is what the mass of three unicorns looks like. This is what the distribution of the mass of four unicorns. This is the distribution of the mass of five unicorns, distribution of the mass of six unicorns, all based on that absurd probability density function, that square and the triangle I showed you up front. And what you see is that when we start adding random variables together to create another random variable, in this case, the mass of 10 unicorns, the bell shape tends to always emerge. And let's do this again. Let's get another absurd probability density function. This is the opposite of what we expect in the natural world, where we have, as opposed to variation clustered around a central value, you have a probability density curve here, which represents a random variable which is less likely to occur near the central value, but more likely to occur sort of step distance away. Let's just say this is something else that might be mythical. This represents the amount of food that the Thor eats every single day. And we add all these random variables together described by these absurd probability density functions. If we keep adding them together, then in this case, looking at the probability density curve describing the amount of food that Thor eats over 30 days, which is the sum of what he eats in day one plus what he eats in day two, etc., etc., etc. So what we know is that when you add lots of random variables together, regardless of how crazy that random variable is distributed before you start adding, you add them together enough, you will get the bell curve every single time. So in this case, to do the sort of mathy bit, y equals the sum of lots of independent random variables, x1 plus x2 plus x3. And the more you add, the more closer it is, y will be more closely modeled by a bell curve. And this is what we call the central limit theorem. And I'll go into that in more detail in the normal distribution webinar. And there's a reason why I have tortured some of you again by going through the central limit theorem. Whenever you add stuff together, you get to see the bell curve. And so let's look at the bell curve in action. Here's a bell curve describing the time to failure of something. The bell curve is really good at describing the time to failure of things like rubber tires. The reason being is that tires, as they are driven on vehicles, they lose on a random amount of tread for every mile or kilometer they're driven. But that tread, be it a random variable, still has its own distribution. And so the total amount of tread a tire has lost is the sum of the tread it's lost through mile 1, through mile 2, through mile 3, so on and so forth. And so we see a bell curve do a magnificent job of describing the time to failure of things like tires. And so here's a bell curve, which is describing the likelihood of lots of data points representing times to failure of something. And I'm going to add to this bell curve a histogram. You can see the histogram of these 1,000 data points relatively closely matches the probability density curve, as you would expect. If we had an incredible number of data points, that histogram would then collapse to create a perfectly smooth curve, which would be exactly equal to the orange probability density curve behind it. I've added the L10, L50, and L90 lives. Now, the L10, L50, and L90 lives of something represent the time when you expect 10%, 50%, and 90% of your items to have failed. And essentially, the L10 life occurs once you have accumulated 10% of the total area under the bell curve. In this case, L50 life is where you expect half your things to have failed. And L90 is when we have taken up 90% of the area under the curve, probability density curve. And what I'm going to do right now is just look at what happens when we look at this data in a different way. So there is 40% of data points between the L10 and L50 life, and the log normal distribution looks like this really weird skewed shape. You can see that what we've done is we've essentially changed the way these data points are modeled. But on the left-hand side, we have 40% of our data points between the L10 and L50 life, but in a very squished, compressed way, in compressed region. On the right-hand side, we have the same thing, but now it's over a much larger region. So we have some asymmetry going on. This is the first tentative step into what a log normal distribution is. So let's have a look at what is going on for said log normal distribution. You note that normal has the word log in front of it to make this log normal. What does that mean? Well, if we were to look at this distribution here, and we add some guidelines grid lines to sort of give some visual representation of the magnitude of the random variable, Let's now squish or change the perspective of which we're looking at this random variable in such a way where we have this scale here. What's going on? We now, instead of having those green grid lines equally spaced, we now seem to have a bunch of green grid lines, but they're certainly not equally spaced. They look like they're being compressed as we move to the right, then stretched out and compressed again as we move to the right. Why am I doing this? Well, this is a different sort of scale. This is a scale where, as opposed to we're going up 1 unit step increase at a time as we move from left to the right, we're going up in ways that appear to be a little bit different. This is where you can see what essentially is happening is that for every step to the right, from red line to red line, we go up by a factor of 10, which is a very different way of looking at data. This is exactly the same data we were looking at, just in a different scale. And you might notice that when we go to this scale, called the logarithmic scale, the bell curve emerged from exactly the same data points. All we needed to do was sort of squish the data points in a way to create this logarithmic scale. So we squished it in some ways and then pulled it out in others. And this bell curve magically popped out of data points that I told you were described by this thing called the log normal distribution. So what does all this mean? Well, this means that another way of looking at this scale is to look at 1, 10, 100, 1,000, 10,000, as opposed to being expressed in terms of full numbers. We can have them expressed in terms of 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. And if we take the 0, 1, 2, 3, 4 in this case, we can look at things in a very different way. Now, if we change it to fives, so the scale hasn't changed at all in terms of what you see on the horizontal axis, but now instead of these green and red lines being based on tens, the green and red lines are based on five. So every time we go from one red line to the next, we go up by a factor of five. And so we go 5, 25, 125, 625, 3,125. And you'll notice that even though we now have the green and red lines based on 5, and the scale on the horizontal axis is still based on step increases of 10, they're actually describing the same scale because the 5, 25, 125, 625, 3,125 are all happily falling exactly where the scale based on a factor of 10 says they should. So it doesn't really matter what your base number is, 10, 5. We can create this sort of ruler for every number we designate as the base, in this case 5. And instead of us going back by a factor of 5, just by using those exponents, we now create a ruler where we go up one step at a time. So 0, 1, 2, 3, 4, 5, and so on, where every unit increase to the right means we're adding as opposed to multiplying. On the horizontal axis, you can see 5, 25, 125. So you're multiplying down there. You can see what those numbers are looking like when you multiply. But for the what's numbers on the ruler, it's essentially what we need to raise the base to get those numbers. And it doesn't matter, again, what base it is. And it doesn't matter if the number is not an integer. So, for example, if we look at 3.5, we draw a line down. That's that 3.5 on that ruler there corresponds with the value of 279.5085, which happens to be 5 to the power of 3.5. So there's a level of consistency here with this sort of ruler action going on. But again, it doesn't matter what base we're using. And if we use a base of Euler's number, which is what E is, it's a very useful number. I've done plenty of webinars where we talk about this number. Euler's number appears so often in the natural world from a mathematical perspective that it's become extraordinarily useful, including in the world of reliability engineering and statistics. So if we look at this scale, instead of being based on tens or fives, but instead now Euler's number, we can also just create another ruler with base E, because E represents Euler's number. And you see now we have a ruler which has those numbers a lot more closely spaced, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 this time. But still, every step increase to the right, you're adding to the numbers on the rulers while you're multiplying to the numbers on the horizontal axis. And so we have, in this case, three different rulers that all represent the same scale. The top one is the ruler with 10 as the base number. The middle one is a ruler with 5 as the base number. And the bottom one is a ruler with E as a base number. You can see the numbers are the spacing of the numbers changes as their base changes. However, you can see they are all increasing by the same amount for every step increase to the right. They all add up, while the numbers on the horizontal axis consistently all multiply. And so what we're doing here is creating what we call logarithms. These numbers are logarithms based on the numbers we designate as the base on the right-hand side. And so we can use these logarithms to help us in the world of probability and statistics. So for example, number 1000, the horizontal axis, if we draw a line up to our top ruler, that corresponds with a logarithm of 3. And so we can say that 3 is the logarithm of 1000 to base 10. If we go to the next ruler, we can say that 4.292 is the logarithm of 1000 to base 5. If we look at the third ruler, we can say that 6.908 is the logarithm of 1000 to base e. And because e, Euler's number, appears so often in the natural world, we actually call this the natural logarithm. So whenever you see the natural logarithm, we're actually talking about a logarithm to base e. So 6.908 is the natural logarithm of 1000. So we have three different logarithms here because we have three different bases. You can create a logarithm for any base that you want to, but the key takeaway is that when you do create logarithms, they essentially add up when the number you're basing them on multiplies on the horizontal axis. And so the logarithmic scale turns multiplication into addition, sort of. And we're going to exploit that by picking a random number to illustrate what we're doing, like 23. We just randomly pick 23. So let's go back to a normal uniform scale where if every step increase to the right, you're adding another number to itself. This is the most common scale we deal with. It's the most comfortable scale where we go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That could be 1, 2, 3, 4. It could be 1,000, 2,000, 3,000. Either way, with the scale here you were saying is not seeing, I should say, is not logarithmic, it's uniform. And so the number 23, if we take step increases to the right based on the number of 23, you can see we go from 23, 46, 69, 92. Every time we add 23, we go one more step to the right. However, if we look at the logarithmic scale and start with the number 23 and then add 23 and add 23, you can see each step gets smaller on the logarithmic scale. And you can see it goes 23, 46. What comes after 46? 69, 92. Is that right? You can see that those numbers in this compressed scale, as the numbers get bigger, the step increase to the right gets proportionally smaller. And so the logarithmic scale isn't about addition in terms of unit steps, but if we multiply by 23, you can see 23 by 23 is 529, 529 by 23 is 12,167. You can see every time you multiply, the unit step increase to the right remains the same. So this is what we're talking about when we say that the logarithmic scale, in a way, turns multiplication into addition. We associate addition with unit step increases to the right because the uniform scale is the predominant way a scale we use to look at things. But the logarithmic scale creates these unit step increases when we multiply, just like addition does on the uniform scale. And so another way of looking at this is that for every time we take a multiplicative step to the right, whatever logarithmic scale we're using, it increases by a fixed number. So 3.315 plus another 3.315 to multiply by 23 again, plus another 3.315 when we're looking at logarithms to using e as the base number. Use a different scale, you can see that the 23 multiplying by 23 step increases result in 1.948 being the logarithmic delta, so to speak, when the base number is 5. And that changes again when we're using the base number of 10. Increasing by a factor of 23 means that the logarithm to base 10 increases by 1.362 as we move from left to right. And so you can see just how the logarithmic scale, in a way, turns a multiplication into how we would look at addition. Now, if we see the bell curve in a logarithmic scale, there is a key thing going on. So, for example, if we plot if we get a lot of data, time to failure data, whatever it is, and we plot that data on a logarithmic scale, and if we have so much data that it allows the histogram to become incredibly accurate and incredibly smooth, and that histogram looks like a bell curve, then essentially what we can say is that we are looking at a random variable that is the product of lots of other random variables. In the same way, if you see the bell curve describing a magnitude without you having to do any special scales, you can say, okay, the time to failure of that tire, which it seems to be described by the bell curve, it usually means that there's some random process which itself is a sum of lots of other random processes. If you have to put your data on a logarithmic scale to see the bell curve come through, then what that means, or what that's a symptom of, is your random variable being based on the multiplication of lots of other random variables. And so that's essentially all the log normal distribution is. When you get the bell curve and the logarithmic scale, it tells you that the random process is based on things multiplying together. And that's a hugely important understanding of where this probability density curve comes from. And so if we bring back our ruler with the logarithms on base e, we can see that this bell curve has a mean or balance point at or around 4.605 in the logarithmic ruler for Euler's number. Now, mu is a Greek letter we often use to represent the mean of something, but you can see here we have this little Greek letter tau as a subscript next to mu in this case. And that tau is one way of making sure that when we write this mean down, we are talking about the mean in the logarithmic space. So mu tau here is 4.605. We look at the standard deviation of this bell curve. In this case, the standard deviation happens to be 0.806. We use the Greek letter sigma to represent the standard deviation. And again, because this is in the logarithmic space and we're basing it on the logarithms, that ruler, we put that tau in there just to make sure we're not confusing ourselves in the future about whether this is the true mean or the true standard deviation. And there's a reason why this is very important, because these are the parameters we use to describe a log normal distribution. If we look at them in the real world, you can see that mu tau, the mean of 4.605 in the logarithmic, using the Euler's number logarithmic ruler, that corresponds to an actual real world mean of 100. And we go one standard deviation to the left on Euler's number logarithmic, on the Euler's number logarithmic ruler, well, that means we go down to 44.93, but one standard deviation to the right on Euler's number logarithmic ruler means we go up an incredible step to 222.55 on the logarithmic scale. So you can see how we have the logarithmic scale on the ruler and the actual magnitude of the random variable on the horizontal axis, and they have some very different behaviors, very different characteristics. And that's very important to understand. So if we look at this bell curve for our random variable. You can see I've added the L50 life, the median life, or a time by which we expect 50% of our things to have failed, and morph back to the uniform scale. Here is the probability density curve for this random variable. This is the log normal distribution. And it's got this weird skew thing going on. It's not a bell curve anymore. It's got maybe a bell shape, but it's not symmetrical. Some things have really changed. The L50 life, which was also happens to be exactly where the balance point was in the logarithmic scale for our bell curve. Well, now the balance point is not the same as the L50 life the way it was, because our probability density curve is no longer symmetrical. It extends way out to the right. If we zoom in to see this difference a little bit better, you can see just how far away from the median the balance point or mean is. And in fact, the three measures of central tendency we tend to use, they are spread out. Whereas the bell curve, which is perfectly symmetrical, the mode, median, and mean are all the same value. And that's because we have a right skew or a right tail for this probability density curve. And so that's a rough and ready introduction to the log normal distribution. The central limit theorem drives everything when we add and multiply random variables. If you have something which is wearing out in a uniform way where the amount of damage adds up over time, it's a pretty good bet. The bell curve is going to describe its time to failure. But if you're modeling the time to failure of something where damage accumulates by multiplying together, well, you might see the log normal distribution. And we're going to look at that in a little bit greater detail shortly. So it's just getting some of the theory done, and this is all in the guidebook. Here are three example probability density curves for the log normal distribution. And you can see that in some cases, the log normal distribution can look a lot like a bell curve. And that happens when the numbers you are multiplying together are close to one. When you have the closer you are to one, the more similar multiplying and adding becomes. So, for example, if you multiply something by 1.01, you increase that number by about 1% every single time. And that will change as the magnitude gets bigger and bigger. But the closer to one, the closer it is, closer multiplication and addition behave. And so sometimes you can have natural processes in the real world that are pretty well modeled by both the normal distribution and the log normal distribution in certain scenarios. And you can see for these three probability density curves, the parameters which define them are on the right-hand side, mu tau and sigma tau. And so you can see that they all have a right skew or right tail. And when we look at these probability density curves in the logarithmic space, you can see that every single time they have that bell curve. And so the red and the orange ones have the same mean in the logarithmic space, but different standard deviations in the logarithmic space. And that creates very different probability density curve shapes on the left-hand side. And another way of looking at it is that we can look at different times to failure, for example, and they should then trace out exactly the same areas when we transform them from the uniform scale to the logarithmic scale. So, for example, the blue one on the right, the bell curve representing the distribution of the logarithms of the random variable in question, when we go 0.6 above and below the mean, that corresponds to when we raise e to the power of those values, 1.916, 3.490, and what's the bottom one? 6.360. When we put those back onto the uniform scale, the area under the curves that these trace out is exactly the same, 68.27%. So even though the shapes are very, very different, they still retain exactly the same information about the random nature of the random variable in question. And so every log normal distribution will have the ability to go the other way as well. The area under the probability density curve between 4 and 8, we take the natural logarithms of those two values and transpose them to the right, then that will also trace out exactly the same amount of area under that curve on the right-hand side. And so the information is perfectly well encoded in each one. And so That's the probability density curve. For those of us who know what the CDF function is, that's the failure function, which is given by the area under each PDF curve. And this tells us the likelihood of something failing by a particular point in time. So we can trace out the area for each one to create our CDF curve. There's the orange one. Here comes a red one. And last but not least, there's the blue one. And these curves on the right-hand side tell us the likelihood of something failing as it gets older, and they all approach one because things will eventually fail. And so it's another way of encoding exactly the same amount of information. And then there's the reliability functions, which are essentially the CDF curves upside down, because the reliability function is all about things that have not failed, the likelihood that things have not failed. And 1 minus a CDF gives us these curves. And so they're just essentially the same curves, but upside down. The likelihood that something is still working. You can see they all start at 1, assuming everything works at day 0, and goes down over time. So that's the reliability function. Then there is the hazard rate, which is the rate at which a thing that is still working fails. This is given by the PDF curve over the reliability function, the probability density function over the reliability function. And when we do that, we create these weird looking hazard rate curves. Now, you can see that these hazard rates curves, which at least initially appear to represent things getting more and more likely to fail as they get older, i.e., this represents things that wear out and accumulate damage, things that get weaker and weaker as they get used. But you can also see that for some reason, one of these probability density curves is creating a hazard rate which goes up, and then it goes down. What is going on there? Initially goes up, indicating accumulation of damage, and then it starts to go down. What is going on there? Well, this is not really possible in the real world of reliability engineering, even though the log normal distribution does describe a lot of things in terms of times of failure very, very well. Certain combinations of parameters will create this seemingly implausible hazard rate. And this means that the mu tau and sigma tau parameter pair of 1.25 and 0.6, you're not going to see them too often in the world of reliability engineering. It finishes by going down. That just doesn't happen. You don't get things that start wearing out, get weaker and weaker, then all of a sudden, once they cross a threshold, start getting stronger and stronger, which is what this curve appears to suggest. It suggests that damage is no longer accumulating, starting to heal itself. So we have to look at this in a different way. This is actually not possible. So we need to understand that this particular log normal distribution is unlikely to represent a real world failure mechanism. And even though there is going to be, in some cases, some log normal distributions modeling failure mechanisms pretty well, there may be some instances where this hazard rate has a temerity to, at least from a statistical or theoretical perspective, go down again. Now, that doesn't mean we throw the log normal distribution away. Far from it. It might mean that the log normal distribution does a fantastic job of describing how things fail initially, and then then the hazard rate then starts deviating away from what the log normal hazard rate might tell us after some period of time. And that is often exactly what we see, because again, in the real world, when things get more and more damaged, the rate at which they accumulate even more damage goes through the roof. And so it's not unusual to see log normal distributions do a really good job of modeling the first significant majority of things failing, but the model's starting to break down for the last 10% or so. And that might be okay, because we are usually only interested in the first 5 to 10%. And so we will often see things like the log normal distribution on the left-hand side being useful for the majority of failures, as you can see, up to a value of about 0.5. And then after that, it doesn't matter anymore. So when do we see the log normal distributions in reliability engineering, I should say?
Hey, Chris, I got an interesting comment from
Oh,
Michael.
cool.
He said, when you're talking about it doesn't happen in the real world, he said, what about concrete? And I asked him, what do you mean? And he says, concrete strength increases over time. Would that be an exception?
That's a really good point, but that would then change failure mechanism fundamentally. So you will certainly have scenarios where, for example, concrete gets gets stronger over time. How it relates to a failure mechanism is that then fundamentally changes the failure mechanism. You need a different model to describe how things fail. And I'm not saying that's cheating. It's just that it means that the log normal distribution would no longer apply, or any distribution would no longer apply if the physical characteristics of a system are changing, albeit in a healthy way. You'd have to essentially remodel and remodel and remodel. And for concrete, that happens. There's a lot of understanding of how strengths and deviations and strengths improve as the concrete cures and gets older, et cetera, et cetera. But that would then change the failure mechanism. But it's a really good point, and hopefully I've done a relatively good job of answering that question. But when the physical characteristics of a system don't change and you have a single failure mechanism, that failure mechanism itself is not unlikely, just not plausible for it to start accumulating damage up to a particular point and then start healing itself. So I'm not trying to fob Michael off, but it's a really interesting phenomenon which applies to a slightly different statistical take, if that helps.
Yeah. All right. And another one just popped up that also seems to apply here is to determine the whatever that word is, the usefulness of a log normal distribution is to fit a failure mechanism. Do we also need to compare it against the hazard rate to make sure the fit applies?
Well, there's lots of different ways you can fit things, and I think the hazard rate is something I wouldn't suggest, because the hazard rate is very difficult to create or estimate empirically. What I mean
Well,
by
I
that
think
is,
I think that's separate. I think that's maybe the wording should be so that the log normal distribution is an appropriate model for it. Because if you get that decrease, increase then decreasing hazard rate, maybe that's like concrete, and you got to look at a different model to deal with it.
well, you'd also see any deviation in the CDF as well. So it wouldn't be manifesting itself in any sort of hypothetical comparison between observed hazard rates and theoretical hazard rates. You would see a fundamental change in the last 20% of your CDF data points as well. So it wouldn't just manifest itself in the hazard rate. That's good conversation, which is sort of be part of a really useful question to ask in a Weibull analysis lesson, Weibull plotting. But
which you're working on.
yeah, that's right. But that's a really good point.
Okay,
But
great.
you'd also see that in the CDFs as well.
All right, that's it.
All right, awesome, good questions. So on things that wear out with an increasing rate, everyone knows about fatigue. Well, not everyone. Most people know about fatigue, and fatigue involves a crack which grows slowly over time. The reason why it grows slowly is because it's being subjected to cyclic stresses. And the crack is a stress concentrator. So the tip of the crack concentrates stresses. And so if every cyclic load, the stresses at the tip of the crack are huge and make the crack just grow ever so slightly. That has the effect of making the next cyclic stress being amplified even further at the tip of the crack. And the next step is just a little bit more. And that is actually a multiplicative effect. When you have the size of the crack essentially dictating how quickly the crack grows, that's a classic multiplicative effect. And you can see that after a good chunk of cycles being applied, this poor old piece of steel or whatever it is in a world of hurt, this is what fatigue looks like. And the other thing too is that when it comes to fatigue, we have a lot of information about how fatigue works. So let's go back to my smart lock that some of you will be aware of. It's sort of my go-to for illustrating concepts. And here is the handle of the smart lock. And the handle is a very simple component, and we're concerned about fatigue cracking from lots of door openings right there. And the reason why is because that is a stress concentrator, the inner radius. So we might do some finite element analysis to quantify the stresses, and our FEA then identifies that, yes, as expected, the stresses are amplified on inner radius of that handle, and they estimate every time someone opens the door by using the handle, stress is concentrated up to 500 megapascals for this steel alloy right there. So that's interesting. So what we can do is then go to a chart like this, where on the horizontal axis we have number of cycles, and the vertical axis we have the stress associated with um, each cycle that's being applied to steel. You might notice that on the horizontal axis, we have a logarithmic scale. Just hold that thought. And the reason why I'm creating this chart is because we are able to create this chart based on thousands of experimental observations for, in this case, 1045 steel. Essentially, we can put steel specimens into test rigs and create this sort of chart where we have a sort of a line of best fit and this sort of blue region around that line of best fit to represent the deviation we observe in terms of times to failure or cycles to failure for steel. And steel alloys tend to have this thing called the endurance limit, very useful concept or characteristic, just means that anything below 300, 250 megapascals, no matter how many cycles you subject steel to, it will just never cause fatigue failure. Aluminum or aluminium, on the other hand, it will always fatigue no matter how high or small the stresses are. So steel has this endurance limit, which is very useful. Now, the first letter of the word stress is S, and the first letter of the word N is of the word number is N. I'm sorry, I'm doing tons of tutorials and stuff, Ram, so my ability to English is not very high. And so this is what we call an SN chart. And you can see this blue region here represents a 90% confidence interval. And the idea is that this SN chart is able to, for example, help us work out how long it's going to take for things to fail. So for example, if we look at 500 megapascals and draw a line across on this SN chart, you can see that it sort of crosses this 90% confidence region where those two red lines are. And you can see there's a bit of symmetry in that space. You can see that the line of best fit appears to be right in the middle of this 90% confidence region. But when we draw lines right down, straight down, you can see it's not very symmetrical. So the lower 90% confidence bound corresponds to about 12,000 cycles. The best guess, the blue line, is about 28,000 cycles. But the upper limit on our confidence bound, or upper confidence bound, I should say, is 63,000 cycles or thereabouts. So you can see there's not a lot of symmetry. The distance between 12,000 and 28,000 is a lot smaller than the distance between 28,000 and 63,000. And this is a classic log normal characteristic. We can in fact see that the natural logarithms of each one of these three tend to actually appear to be very symmetrical, in that the natural logarithm of the best guess is about 10.2, and the natural logarithm of the lower confidence bound is about 9.4, and the natural logarithm of the upper confidence bound is 11.06, with 10 being right in the middle. And this is because when we look at these curves, essentially we see this bell curve as we move from left to right, describing the likely times to failure or likely cycles to failure for 1045 steel. So the SN curve, based on tons of experimental data, essentially highlights and illustrates a log normal distribution when we see this bell curve appear in a log normal scale. And so that is now very, very helpful. Then we have the 10.23, the natural logarithm of the mean of this bell curve. There's our log normal distribution parameter, mu tau. And we have 9.4 and 11.06. That corresponds to the upper and lower confidence bounds when we are for 90% of the area under the curve. And so 90% of all random variables are within 1.28 standard deviations, which means that we know that the distance between those two values of 1.64 corresponds to two lots of 1.28. So 2.564 sigma tau corresponds to 1.64. Do the math, it means that sigma tau turns out to be 0.6396. And now we have the parameters for a log normal distribution. And so this SN curve, which is often used to give us a best guess, a point estimate of times to or cycles to failure for fatigue scenarios, now we can actually get the or estimate the log normal distribution parameters, mu tau and sigma tau, we can assume the log normal distribution does a really good job of describing times to failure for fatigue because we know that fatigue has a classic multiplicative effect. And we can create this log normal distribution, which does a way better job of helping us understand when our door handle is likely to fail. We don't just have a best guess of about 28,000 cycles anymore. You can see there's quite a bit of variation in terms of how long we think it will take for this thing to fail. If you were to make decisions based on the best guess of 28,000, you can see just how much of this probability density curve lies to the left of that 28,000 figure. So there's a ton of variation that doesn't immediately jump out at you when you look at the SN curve, but it does jump out at you when you take those parameters and create a much more informative log normal distribution and plot that PDF curve to have a look at. And when you do, you can see just you got an incredible amount of information to help you work out what warranty periods should be, if that's long enough or not, the likely fraction of door handles failing in the certain warranty service life scenarios, etc., etc., etc. Now you can actually generate some really useful information, and that starts with us understanding how um, how fatigue actually causes things to fail based on the multiplicative effect on the amount of damage that you accumulate. But we're not just here to admire problems. And what do I mean by that? Well, if we look at this handle here, what sort of things can we do into the design or manufacture to reduce the likelihood of fatigue failure? Well, we can look at if we believe fatigue is a dominant failure mechanism for our current design. What we could do is do things like in place rubber stoppers, increase handle cross section, shot penning, increasing inner radius, surface polishing, material selection, decreasing manufacturing defects. We can do, for example, if we look at increase in the inner radius, we can do that in a way that will hopefully reduce the stress that each cycle exerts on our handle to the point where the stress is below 250 megapascals, to the point where fatigue is no longer a concern. So we shouldn't get too enamored with statistics, even if we are pretty proud of our efforts, and we should be, because log normal distributions can be tricky to understand, but hopefully you understand them a little bit better now. But let's not forget that if we are looking at a handle and we're concerned about failure due to fatigue, let's just see if we can reduce the stresses that are concentrated at the inner radius to the extent that fatigue stops being a concern for us. But if we can't, then we can use the SN charts and finite element analysis in order to characterize the likely stresses and create an incredibly powerful, incredibly informative log normal distribution to help us make much better decisions. So measuring reliability is important, but not nearly as important as making reliability. So as a slight aside, we've also found that the log normal distribution is really good at modeling corrective maintenance time. Now, as opposed to being able to describe the mechanisms beneath this, it's just
Chris,
sorry?
a quick comment that goes back to that SN curve just came up is John said, I just realized how to estimate SN confidence intervals using MMPDS charts, which I'm not sure what that is. They typically provide an empirical relationship to estimate sigma, the NF. It has two stress concentration factors converging at a point. We try to separate those geometries. So, not all that familiar with what he's talking about there.
It has two stress concentrating factors converging at a point. I'd like to separate those geometries. I think that's more along the lines of the actual geometry informing a hypothetical model about the magnitude of the stresses. And they typically provide an empirical relationship to estimate the sigma. And I think you're talking about the sort of the notches and things like that, that shapes that but concentrate stresses. I think if that's Johan, I'm more than happy to hang around after the webinar's over to talk about that. But I think that's a slightly different topic, although it's not a million miles removed. I think it's about the mechanisms for us understanding the magnitude of stresses versus the failure mechanism itself. Is that a fair call, do you think, Fred?
Yep, yep. And he just added, sorry, 2 comments on 2 different subjects, just musing aloud. So Johan, if you have time, hang out afterwards and we'll Chris
We'll have a
probably
chat,
dive
yeah.
into it.
But sorry, going back to this, what's on the slide right now, we found the log normal distribution is really good at modeling corrective maintenance times. There's no beautiful explanation for this. It's just been found it just is remarkably accurate just by observation. And that, in a way, makes a little bit of sense because the log normal distribution has a right tail, and that right skew or right tail. And so that, when you think about corrective maintenance or repairs, we often have lots of repairs that don't take very long. And every now and then we have 1 or 2 repairs that take a long time. And then when we have maybe a moderate amount of repairs that take a certain amount of time. But because we tend to have lots of repairs that take not long to complete, we often see this skew effect where we have a higher probability density for lower corrective maintenance times because the frequency is higher. But we will always have those scenarios where we have to pull the entire chassis apart, so to speak, and put it back together, which take weeks or months to do. So we have this right tail effect. It's just been found that log normal distribution is remarkably good at modeling the distribution of those repair times or corrective maintenance times. So that's another thing the log normal distribution can help you out with. Now, on that note, are there any questions besides what Johan's talking about? In which case, but because we're going to talk about that after the conclusion of this conversation, are there any questions? I can now pull the chats across and maybe have a look at them myself. Oh, I've got 44 attendees. 42, if you don't include me and Fred. Any questions? Any comments?
Yep, there's over on the Q&A, which unfortunately I don't tend to pay much attention to. And there's one from Carl on the comments. It's can you go over the difference between mean and log mean?
Yes, I see that. The mean and the log mean. So just bear with me while I try and let me just try and get back to one of my previous slides. Sorry about this because I only have a single slide here. Let's go back to can we see that one there?
Yep.
So you can see on this slide, we have, once we put our random variables into the logarithmic space, we get that bell curve. And the scale of that random variable is on the horizontal axis. So 1, 10, 100, 1,000, 10,000. The ruler, which contains the logarithms for those values to base E, is also seen. So you can see that the logarithmic mean, in this case, is about 4.6, but that corresponds to a random variable value of about 100. So once the log mean is essentially the mean, once we transformed it back to logarithmic space and we're just using the logarithms, nothing else. And so the balance point right there which is how we define the mean, the bell curve, it's lovely and it's symmetrical, so it makes it really easy. The balance point corresponds to a natural logarithm of 4.605. That's the log mean, remembering that in the real world, this is a random variable value of about 100. So once we go through, I'll quickly go through and morph back to, so you can see there, the mean corresponds to a value of, the real world value of 100. The log mean in base E is 4.605. Remember, the mean is just the balance point. So when we morph to the corresponding log normal distribution, the balance point is no longer corresponding to a value of 100. In this case, it's about 138. So the L50 life, just so you know, that's the value of 100. That's equates to 100. The balance point is to the right. So the log mean is essentially the mean of the logarithms, and the mean just refers to the balance point of the actual or raw random variables. Hopefully that helps you, Carl. Thank you, Sebastian, and Kevin. Thank you very much. Yeshwanth, sorry if I haven't mispronounced the name. So if I encounter a failure with a mixed failure mode, then would it make sense to focus on the log normal distribution first, or any other steps before deciding on the log normal distribution? In that scenario, the scenario you're describing is something you would need to look at slightly differently. Maybe look at Weibull analysis webinars we do to work out which one of those failure mechanisms or failure modes is dominant. If you're interested in early failures, then one failure mode or mechanism will typically dominate early on, if then it does indeed be replaced by something else later on. So it depends on which one is dominating at the point of time you're interested in, and Weibull analysis can really help you separate out those failure modes and failure mechanisms. And once you've done that, you can also then, once you have those separated data points, then see if the log normal distribution applies the ones you split. But that's subject to a broader discussion and separate webinars. Paul writes, when the log normal fit is better than the Weibull fit and the failure mechanism points to log normal, what are the downsides of using the Weibull anyway? When it comes to fitting distributions, I never like doing something which doesn't make physical sense. So before I do analysis of any type, I want to think through what the dominant failure mechanism I think is. So if I'm looking at dielectric breakdown, I've got data there. I sort of know what sort of failure mechanisms drive dielectric breakdown. And I would then, because I've done this a fair few times, I'd say, okay, that's likely going to be described by a Weibull distribution with shape parameter of X or what have you. And so before you do any statistical analysis, always take the time to think about what you would expect based on your understanding of how things fail. You should never just do statistical analysis without trying to understand. So for example, if you're modeling something and you suspect fatigue is causing failures, and you see something which is pretty well modeled by the Weibull distribution and or log normal distribution, you might just go to the log normal distribution because you know that also combines with your previous understanding of how things fail, is a likely candidate for describing how things work. What you don't want to do is just chop and change between different distributions because one fits slightly better than the other. When that happens, you need to be quite careful making quite careful in terms of just picking the one that on that day fits best. That being said, the Weibull distribution can approximate the log normal distribution pretty well and can be used pretty comfortably to model a lot of fatigue scenarios, especially when you're concerned about the first small fraction of things failing due to fatigue, which we typically are. The Weibull distribution, when it approximates a log normal distribution, the hazard rate also doesn't have that annoying little decrease after a certain time. So that's a positive for the Weibull distribution. But I'd take a lot more into consideration than just the p-value or the goodness of fit check test that a software company says helps or creates to help you drive your decision. Stephen, thank you. Thank you very much for that positive sentiment. Julie, thank you. And Yeshwan, thank you very much. Sorry, that was questions.
Over in the questions tab, Carl had a couple of them, and I didn't chime in earlier because I knew you were going to answer a good number of these. But the first one was, what's the significance of a log normal distribution, which I think you covered pretty well. Mm-hmm. What is the log normal distribution in the reliability analysis? I think you were just talking about that. And among other things, what is the limitations of log normal distribution? That one I don't think you covered too much.
Yeah, I think the limitations of log normal distribution or any other distribution are when the premise breaks down. And so I think one we talked about was whether hazard rate does its own thing, which
Mhm.
again makes sense because when you have fatigue failure, essentially the crack doesn't work its way slowly and steadily through the entire specimen. It gets to a critical length and then all hell breaks loose after that. So the hazard rate just essentially goes through the roof. So that's one shortcoming per se. And the other one would be I think that I wouldn't describe that being a limitation of the log normal distribution. It's just the characteristic is that it does model things that multiply together. So when that presumption or that basis evaporates because like the fatigue crack hits that critical length, then of course the log normal distribution stops being helpful. But I'd essentially characterize the limitation in that way and leave it up to you guys to work out when that premise breaks down. And I think we also covered why we use a log normal instead of normal. Things multiply, log normal. When things add, normal. Okay, a few more comments coming through.
Yeah, it looks like Johan's not going to be able to stick around. So
Right, but he's going to email. That's fine. And for those saying, "Where's the PDF?" It's in the. I think Fred's shared the link a couple of times, and it should be online too.
well, give me time for that.
That's what I mean. I mean, sorry, for those who can't get it today, it will eventually be on the Ascendo website. I need to go now, recover, and regain my ability to speak English.